Alrighty, Michael Strevens, we are live with your new book, The Knowledge Machine, How Irrationality Created Modern Science. Thanks for coming on the show. Love to talk history and philosophy of science with a professional in the field. And so before we get into all that, just let's start with just giving us some background. Where were you born and raised, and where'd you go to college? What were some of your mentors or people that inspired you to go into philosophy and philosophy of science, and how you got to where you are now?
Sure. Yeah. Well, I was born in New Zealand and I grew up there and I went to college there. I originally thought of myself as a scientist and intended to go into science, but somehow I was diverted by personal computers, which just erupted onto the scene around the time that I was an undergraduate or a little bit before, and I got carried away and kind of ended up in the computer lab, not the physics lab. Uh, and by the time I regained my wits, physics had passed me by, and I ended up in philosophy, but as a philosopher of science. So after a few more years of studying philosophy in New Zealand, I came over here to the US to do my PhD in philosophy, and as you say, I became a professional philosopher of science. So now I think about science from the sidelines, you might say.
Yeah, right. So I think where I'd like the conversation to ultimately end up would be to talk about why we should trust and believe scientists at all. As you know, we're in the middle of this kind of crash in trust in traditional institutions, the media in particular, but also authoritarian institutions, not just the church, but also science itself. Why should I believe Anthony Fauci when he's changed his mind 27 times on masks and vaccines and so on? I don't know who to believe. And here I don't mean climate deniers or vaccine deniers that are political or ideologues. I mean just people that just like I don't even know who I should trust anymore, right? So, but before we get to there, just kind of give us a description of how science works. What is it, and you kind of have a different use of the word irrationality. Most of us think, well, no, scientists are rational, like Mr. Spock. So what do you mean by that?
Yeah, well, I do think, well, scientists, of course, are human beings. Sometimes they're rational, sometimes they're not. The irrationality in my subtitle is not something I so much apply to scientists, but to something about the framework, the organizational framework of science. But it's a thing that actually makes science more powerful. So part of the point of writing this book is to explain, well, to show that science is a very unusual thing. I think it's a piece of, if you like, of social technology that was developed only very recently in the last few hundred years since the scientific revolution, that is not simply an amplifier for all of our most rational, reasonable tendencies, although to some extent it does that, but which adds something on top of that, which is, as I put it in the book, a kind of irrational narrowness, but a kind of irrational narrowness that focuses people who are trying to think about how the world works, the people who have always kind of, as it were, been scientists even before the word was invented, focuses them on something that makes their inquiries really remarkably effective and much more effective than any kind of thinking about the world before modern science came along. So on the one hand, I'm praising science, so I very much fit under the heading of someone who will defend science. But on the other hand, not in the usual way, by pointing to the logical or objective side of science, although that's there too, but by pointing to the strangeness of science and the ways in which it's unusual and difficult to come to terms with, the ways in which I think, in some ways, have it's politics as well as everything else, but to some extent, the weirdness of science has been a part of what has led to the confusion and, in some cases, the mistrust about what to do with all of the scientific knowledge, or in some cases, half knowledge that we've created in the last few hundred years.
Yeah. So the methods of science are pretty new, but to what extent are parts of it actually just evolved in our cognition. Sagan made this point in Demon Haunted World that, hunter, and then Pinker ran with this in his latest book, Rationality. Hunter-gatherers tracking game are really kind of hypothesis testers, like, okay, the hoof prints are there and the sun is over there, the shade and the water's over there, so I'm predicting that they would go that way, and then they test the hypothesis by going there and then updating their priors with more information from the tracking and so forth. And that's the kind of cognition that science ends up using. Although, like, by contrast, people are not naturally Bayesian in their reasoning. I think all the time we don't want to disconfirm our hypothesis. We want to win our case, and we're more like lawyers, right? We don't try to find the evidence that doesn't fit our preferred beliefs. We just engage in motivated reasoning and so on. So I'm not sure. I'm kind of conflicted myself, so I'm just sort of free streaming here. That kind of tension between how much of it comes natural, how much of it is totally not natural.
Yeah, I think that the aspects of thinking, which obviously have an important place in modern science that you just described, have in fact been around pretty much forever. It gets pretty speculative when you go back to prehistoric times, but at the same time, it's hard to see how our forebears would have survived without thinking that way. But we have a lot more to go on when we look back at the historical record, still well before the advent of modern science. One thinker I like to go back to in particular, because he was such an impressive scientist in a certain sense, is Aristotle. Best known, I guess, as a philosopher, but someone who wrote hundreds and hundreds of pages on physics, on what we would now call astronomy, in particular on biology, who really was interested in the way the universe worked, in the way the material universe worked, exactly the kinds of questions that modern science too tries to answer. Why do things move? Why do the planets go around? Well, in his case, he thought they went around the Earth. What are rainbows? What explains rainbows? Meteors? What are they? Exactly the kinds of questions that would prompt anybody today to go into science. Aristotle was asking those questions, and he was answering them in ways that are very reminiscent in many ways of modern science. He is trying to find theories that provide explanations in the same way that your hunter-gatherers are looking for, as it were, the best explanation of why the branches are broken in this particular way in order to figure out what animal has passed by. He's thinking that way. He's very much attuned to observation. Of course, he's trying to explain observable phenomena, but he's also denouncing his rivals because they're not paying enough attention to the observable facts. They're not concerned enough to fit their theories to the observable data. He's very thoroughgoing and systematic. He wants it all to fit together. He's thinking really hard about how to get it all to work. It looks in so many ways like modern science at its best, taken as a whole. And so you might very well wonder, well, what, if anything, was missing? Is it just that he needed telescopes or test tubes or large government grants to make progress? And I think the answer is nice as though all those things were. None of them was what was really missing from the Aristotelian program. But there was one thing missing. I'll stop talking here, but inviting you, of course, to ask me what.
Well, yes, what? But do tell. Well, but do tell in that context of why did it start there in ancient Greece? What's the explanation for the miracle of Greece and Aristotle, Socrates, all the, all those great minds? All of a sudden, there had to be great minds before, just statistically speaking. How come it happened there and then?
Well, that's not something I have any story about. I have a story about modern science, how the thing came along that I said wasn't there in ancient Greece, but why it was that little place, rather sparsely populated, really, compared to many parts of the world, even at the time. Why so much sprung up there, I really don't know. Obviously, something unusual was going on.
Yeah, but do tell us what's the.
But it was, I think.
Drop the other shoe there.
I think it was not till 2000 years. Yeah, it wasn't until 2,000 years later that one further thing fell into place, and it was only then, really, that we see modern science having the enterprise that has the kind of progressive power that modern science has. So Aristotle said a lot of really interesting things, but somehow his theories were not built on in the same kinds of ways that, say, Newton's theories were built upon. And I think there's probably a number of different reasons for this. Of course, history is a very complicated time. So there's always many things going on at once. But the single most important thing, I think, is this. So I'll say something about modern science that was not true of science in Aristotle's time. In modern science is not just focused on observable evidence, exclusively focused on observable evidence. So Aristotle is very much trying to make sense of what he sees around him and using what he sees around him to sift the better theories from the worse theories. But at the same time, he's philosophizing. And and I don't say that in a pejorative way. Naturally, I'm a philosopher. But he's thinking about the materials at his fingertips in a philosophical way. He's looking for causes and explanations that make philosophical sense to him, as well as causes and explanations that actually do a good job of predicting or let me just say predicting the things he says. And although I don't think in any way he could have foreseen this, that leads him and his contemporaries and the people who came after him astray in various ways. It turns out that what was really necessary for modern science was what, and here's my other great hero, I suppose, what Newton did, which was a very austere and narrow thing, which completely pushed away all these philosophical questions. Newton said, never mind how gravity works. I mean, he was, in fact, himself interested in it. But for the purposes of officially presenting his theory to the world, he said, never mind how gravity works. What I'm going to do is present you with some mathematical principles that get the phenomena right, that make the right predictions. And I'm doing this in a spirit, the spirit of, as he called it, experimental philosophy, was his name for it. Where we, in fact, don't do any philosophy of the Aristotelian form. We don't think about what are intelligible explanations versus unintelligible explanations. We don't try to fit together our science with our theological beliefs, even though Newton had copious theological beliefs. He was interested in all this stuff, but for some reason, he just zeroed in on the ability of his models to explain the precise details about, in particular, the orbits of the planets and the moon. And that turned out, again, I'll say, it's not that anyone could necessarily have foreseen how successful this would be, but that turned out to be the key, to just focus 100% on experiment and leave the philosophy completely out of the picture altogether. It created a kind of a possibility for a kind of cumulative form of inquiry where all that mattered was the facts, or at least as far as we can discern them, the various theories people have put on the table, attempting to explain those facts, and the fit between the theories and the facts. And that's all that science, this empirical inquiry, became. And that turned out to be what has been over the last 300, 400 years so successful.
Right. So, I mean, Aristotle's physics was kind of a folk physics. It's what you see, like the arrow flying through the air has impetus behind it, pushing it. And then, the impetus weakens and the arrow falls in this sort of, arc. And that is what you see. And so when Newton says, well, no, actually, if there was no air, it was just in space, it would just go on forever until something acted on it. But you never see that, right? Where would you ever see that on Earth? So, I mean, is that what you mean by irrationality? It's kind of counterintuitive. It's like, I don't even know what you're talking about. What do you mean go on forever?
Now, what I'm getting at with the irrationality is this kind of narrowness that is inherent in the project of completely ignoring everything but the observable appearances. So, I mean, I'll back up a little bit. I think Aristotle's physics, if you, approach it as really trying to get into Aristotle's head, is also in certain ways unintuitive. It's an esoteric philosophical construction that takes a lot of thinking to kind of assimilate and begin to understand, to begin to see how Aristotelian physical explanations work. But philosophy was like that, has always been like that. That counterintuitive has always been a part of philosophy ever since the pre-Socratic Greek philosophers were arguing about whether really there was any change in the world at all, or whether everything just wasn't, there wasn't just a single unchanging thing with all of the all of what we see around us just being a kind of illusion. That sort of uh, uh, perverse but enjoyable and intellectually thrilling counterintuitiveness has been around forever. So I don't think that, even though that's an important part of it, was important that Newton was willing to advance these ideas, although in that case, following in the footsteps of Galileo and Descartes, that too was not something new. It was rather a kind of renunciation of any kind of philosophical test, any test for the intelligibility of an explanation, and just 100% focus on getting the predictions right. So that's not that trying to get the predictions right, of course, is a reasonable and rational thing, but I think shutting out all other considerations, first of all, is very narrow, and it's a far narrower way to conduct inquiry than the way that, say, Aristotle or any of the many scientists who have existed before the scientific revolution, the Chinese scientists, the medieval European scientists, the Islamic scientists, and so on. It's much narrower than anything they were trying to do. And I call it a kind of irrational narrowness. I can talk a little bit about why I think it's positively irrational, but in a way, the more important thing is that it was unusually, strangely narrow, this proposal to focus on the data alone. And I think it takes some, one reason I call it irrational is to really press the point, because we're now so used to science proceeding that way, it seems kind of normal. How else would you organize empirical inquiry? It's Aristotle who seems strange. But for thousands and thousands of years, it was not that way at all. Anyway, it was that. So I see that narrowness built into, if you like, the institutions of science. It was the way Newton presented his ideas that was narrow in this way, not his own personal thinking. That's the innovation that made modern science, and that at the same time builds in a kind of, I would say, unreasonable narrowness, which has turned out to be so effective because it's so much concentrated scientists on little clues, little slight discrepancies in predictions and so on, in that particular orbit of that particular planet, or and such like, that have turned out to really be. And I think, this would have astonished Aristotle. Those little details have turned out to be what has really enabled us to distinguish between big ideas about, for example, gravity, whether Newtonian gravitation is real or whether Einstein's story is better.
So would an example, I think I got that.
The secret.
Would an example of this be something like the problem of gravity? What is it? Well, it's the tendency for objects to attract to one another. Well, why do objects attract to one another? Well, because of gravity. Well, then you're just in a tautology, and that's not going to get you anywhere. So you're saying Newton said, okay, don't worry about any of that stuff. It's a force or whatever. I don't know what you call it. Forget it. Just what does it do? Okay, what if you have an object of this mass and that mass, and here's the mathematical equation, describe how they will interact. That's all you need to know.
Exactly. And so all Aristotle, Descartes, so many thinkers before Newton had thought the right place to start is through a kind of intellectual exercise, at least a partly philosophical exercise, to figure out what kind of thing could possibly be responsible for that force. Newton says, I'm not going to start there. And in fact, by the time he was writing up his results, it was pretty clear he was not himself going to have anything further to say about gravity. I'm going to finish just by giving you this predictive system, so we'll know, as you put it very nicely, what it is that gravity does, even if we don't know what gravity is. And that I think was the power move in the history of empirical inquiry, which showed the way forward for a kind of a form of thinking about the way the world works that became modern science.
Right. Do you have a story for why
it's a kind of profoundly
why it took 2,000
unphilosophical form?
Yeah. Do you have a story for why it took 2,000 years to get from Aristotle to Newton? Or maybe if you want to start a little bit earlier with Galileo and Copernicus and so on, just the whole scientific revolution. Why 2,000 years? Why didn't it, go 500 AD or something like that?
Well, I think it's because of the narrowness that seems so unreasonable. If you'd said to Aristotle, look, don't try to think about what kind of thing could possibly explain motion. Just try to get the movements right, he would have said, what are you talking about? Of course I want to get the movements right. That's not news to me. But I also want to be able to think about what is a intelligible cause of motion and what isn't. And you're telling me I'm not allowed to do that? I'm not allowed to bring that into the argument? Go away. You're making no sense. It's not as if the narrowness is forcing you to have any particular view about that. It's prohibiting you from thinking about it at all. And that, I think, would have seemed if Aristotle had considered such a possibility, and as far as I know he didn't, that would have seemed kind of crazy. And likewise to the medieval scientists, whether in China or the Islamic world or in Europe, it would have seemed crazy. Newton was a little bit crazy, I think. And for some reason, I don't really know why, he he decided to proceed in this very narrow way. Um, and that very strangely turned out to be incredibly successful. But for the rest of the world, at the time of the scientific revolution, I think it was Newton's achievement that showed the power of this method. And so it was only once somebody had not only tried it, but in Newton's case, kind of done as good a job as anyone ever has in the history of science of building a theory along these kind of narrow, unphilosophical grounds. Only then were people able to look and say, wow, that worked really well. I want to be like him. And that's how thinkers began to get the idea of organizing science along these narrow lines.
Yeah, I was writing about Newton in the Moral Arc when I was talking about the rise of the Enlightenment, in which almost all fields wanted to have their Newton, like biology and medicine and even economics. It's a system like a solar system that has mechanical parts, and we're going to treat currency like blood flowing through a body or whatever, and that it's all that same kind of Newtonian mechanics. Don't worry about the underlying causes or whatever. What can we predict what the economy is going to do if we tweak these variables, or what the body's going to do if we give it this substance, that kind of thing. That's a very Newtonian way of thinking.
Yeah, and so I think, it didn't have to turn out, or at least we couldn't have expected in advance that, say, in biology, doing things the Newtonian way would be right. So in biology, it would be something like this. It would be kind of abandoning any kind of philosophy of life. Not thinking so much about, whether there could be such things as vital spirits and so on. Newton himself was very interested in these questions too, but although there was a certain amount of that, of course, went on in the history of biology, what really turned out to be successful was, first of all, simply building a kind of a classification system, the way Linnaeus did, doing a kind of careful anatomical work, the way that the various physiologists did. Eventually doing careful geological work, building up the story of the history of the work and the strata of rock and for the purpose of biology, of course, the fossils in those strata. All of this was what really laid the foundation for later achievements, perhaps most obviously Darwin's theory of evolution by natural selection, but it was careful empirical work that wasn't driven by, well, at least it wasn't beholden to, maybe I should say, some particular big philosophical explanatory agenda, some conception of what life is or what's driving adaptation, but just kind of getting the facts into place, just assembling the facts. Those facts look very different in biology than they do in physics. Instead of a bunch of numbers, it's a bunch of life forms, basically. But nevertheless, the same approach works again in biology, works in geology, and so far has worked in all the sciences, or at least I suppose you might say the sciences have only so far discovered what can be discovered by proceeding in that way, which is a lot.
Yes. Yeah. I think of it as a three-legged stool. You need data, theory, and then communication. You have to get your ideas out there, and you need all three. But so what you're arguing is that the initial part anyway is just gathering all the data. What do we know? Before we dive deep into theorizing about stuff, we need just a lot of data, or else we're going to be shooting in the dark. Feynman has a funny story. He tells in one of those long interviews you can see on YouTube where he's sitting in his chair talking about stuff, and he says, people ask me, are you trying to understand, the deepest cause of the universe? And he's like, no, I'm not. I'm just trying to solve one little problem right there, that one little thing. And he's working on his math equations or whatever. I'm not trying to figure everything out. And and that's how he won the Nobel Prize, right? The Nobel Prize is given for solving very specific problems, like Einstein's won for Brownian motion, this little technical problem in physics, and not for general relativity, not because he overturned whatever he did with Newton, added on to Newton, not for that.
Yeah, that's a wonderful example of what I'm talking about. There you have Feynman, who obviously is one of the great and important physicists of the 20th century. And the way he's conceiving of what he's doing is not kind of getting together a big picture the way someone like Aristotle would, but taking a rather specific empirical problem and then applying, well, in his case, a lot of fancy mathematics. But still, the thing was to get that problem right, to really obsess about getting these numbers to come out right, rather than to be building a big picture of the way everything hangs together. I mean, what we want in the end is that big picture, of course, but it turns out the way to get it is to obsess about these little problems.
Yeah. Dawkins likes to talk about it. Well, why did it take so long from Aristotle to Darwin to figure out natural selection? It's not rocket science. It's a pretty simple idea. Huxley famously said, "Why didn't I think of that? It's obvious once you hear it," right? But maybe it took centuries of exploration and collecting species and typing them out and classifying them in a way like Linnaeus did, and having 100,000 bits of data that you then look at and go, okay, let's see if we can draw some generalizations from this massive data. And maybe that just takes centuries to do.
Yeah, I think that's really right. You're right. To have the idea of natural selection, you don't need telescopes, you don't need complex apparatus, you don't really need anything at all, right? Except a natural environment, and everyone had one of those. When I think of the question, I mean, say a narrow question, why was it Darwin who came up with this idea? I mean, of course, we're never going to be able to give a complete answer to a question like that. But one thing that's really striking about Darwin is how much evidence he personally had for various reasons. He'd had the good luck to have been able to go on this 5-year trip around the world on the Beagle. He was the kind of observer who was just interested in everything and sort of noticed everything on that trip. But then on top of that, and all credit to him for this, he looked at the breeders who are doing artificial selection for various sort of showy properties of pigeons, the same way dog breeders create strange breeds of dog. So he's really interested in accumulating that. And he, for example, he embarked on this long systematic study of barnacles in the wake of the discovery that they were really crustaceans, not mollusks, and wrote this big study of the barnacles. Here is somebody who was obviously a big thinker many times over, but who also, for whatever reason, was just absolutely fascinated by the empirical detail. And although I certainly can't prove it, to me it's very likely that was the real advantage he had over the many other biologists at the time who were also trying to answer this question about what could be responsible for the kinds of change, the kinds of evolution they were seeing in the fossil record.
Yeah, he kind of figured out natural selection about 1837. He got home in 1835 from the Galapagos. He opened his notebooks and so on. You kind of track it. Janet Brown does this nicely in her biography. But then I think it was Chambers' book came out in 1844 that was very theoretical about evolution. There were many theories of evolution, and that book was panned by professional scientists. And one of Darwin's mentors, forget who it was, it might have been the botanist, I forget who it was now. Anyway, said, don't do that. Be careful, spend some time, collect a lot of information, have just so much evidence before you just throw it out there. And he did, and he would have taken a lot longer had Wallace not written him. I wrote a biography of Alfred Russel Wallace, right? So I know that whole story about where, Wallace himself, Wallace itself had spent, 5 years in the Amazon and 7 years in the Malay Archipelago. I mean, that's 12 years. And when you read his notebook, it's like, oh my God, this guy's out there like 12 hours a day, just pounding the dirt, collecting specimens, and then, just kind of slowly figuring it out. It's not like Like Einstein has a dream. Oh, okay, I
True.
figured out relativity. It just doesn't work that way.
Yeah, yeah, yeah. Right. I was wondering if I should mention Wallace as well, but
Yeah.
um, again, that's somebody who, as you say, was immersed in the detail of life. Also a big thinker, obviously. In the Chambers book on evolution, natural selection isn't really playing a role at all. It's sort of some kind of everything is infused with God's will that it become more complex and more perfectly adapted to the ecosystem, and um, that, of course, is not Darwin's idea at all.
Right. And to your point, Darwin nor Wallace had a mechanism for natural selection. No, they didn't know anything about genetics. I mean, it wasn't until Crick and Watson in 1953, almost a century later, is like, oh, so that's how it works. So you could have a viable science without an underlying mechanism, right? We don't know what's in the black box right there. We just set that aside, and we'll figure that out later. But these are the predictions you can make, and you can test them.
Yeah, it's often been a kind of an uncertain question exactly to what degree the lack of a mechanism is a problem. Um, so I've really emphasized the importance of not philosophizing about the mechanism, but when you're talking about things, not gravity, but things that happen on higher levels, of course, you can do the empirical science of the mechanism. Um, in my book, I talk a little bit about continental drift and
Yeah,
the
good
great
example.
ructions about continental drift in the early 20th century, when geologists could see that really dramatic things had happened in the Earth's past. So it wasn't crazy to think that the Earth was a very dynamic kind of planet, but still they were absolutely speculating more with very little evidence. Someone like Wegener, who was the great proponent of continental drift, really didn't have any evidence pointing towards any particular mechanism as a serious contender. And that was perceived as a big problem. If you're going to say the continents move, you'd better have at some story, have a good story about the mechanism. And the inheritance mechanism turned into quite a big problem for natural selection as well. There was this, as I'm sure you know, there was this period that who called it this. One of the later biologists looking back, this period called the eclipse of Darwinism in the late 19th century, when various kinds of problems, including the problem of finding an inheritance mechanism that would really allow the brilliant idea of one generation to be passed on to the next, really started to eat away at people's faith in natural selection as a mechanism. So I want to say on the one hand that science works really well when it runs ahead and isn't forced to talk about underlying mechanisms to tie everything together. But on the other hand, it would be possible to overdo it. It's not true that scientists don't worry about these things. I think probably what it requires is a kind of something of a range of different scientists, some of whom, like Wegener, are happy just to assemble the evidence and not worry about the mechanism, or Darwin, who was a bit worried about inheritance, of course, but still stuck to his guns, and some who are really pushing them on these problems.
Yeah, so use continental drift and plate tectonics as an example. So Wegener's in the 1930s, and it isn't really accepted until the 1960s and early 70s, where it's pretty obvious there's a convergence of evidence and a consensus among scientists. Yes, this is what's happening. How did that unfold? The combination of data and theory, say.
So the great discovery, which really brought on the whole theory of plate tectonics and so on, was the mechanism of seafloor spreading, where the rock comes up from underneath, and in places like the mid-Atlantic ridge running down the Atlantic Ocean north to south, and pushes apart the two sides of the Atlantic, and therefore the continents that are sitting on the plates on top. And so the evidence for that was converging evidence from from several different places. And this will allow me to go back and bang my empirical detail table again. On the one hand, evidence simply from mapping the ocean floor, much of which was accumulated using, well, I guess at that stage, maybe all of it came from using sonar systems, which had been developed during World War II, but which one of the first seafloor mappers actually, I think this was the geologist, Harry Hess, was also the captain of a boat in the Navy with sonar on board, and he says he had the idea of just leaving it switched on as they cruised around and building up this map of the ocean floor, not for military reasons, but just to kind of see what's down there, to get the detail. And then a completely different source of evidence had to do with the magnetization of the rock in the seabed, which again required a team of people who were just really interested in looking at the magnetization of the rock in the seabed, as well as some rather sensitive magnetometers. So there too, you have this big idea, the mechanism of seafloor spreading, the whole idea of continental drift, of the theory of plate tectonics, and where it really gets its grip is not from the construction of a big picture, but from this very detailed empirical evidence, which by itself doesn't seem very interesting at all. I mean, I guess it's kind of cool to have a map of the ocean floor, but but you wouldn't spend, in this case, that kind of came for free, but to spend millions and millions of dollars putting together that map, you would have to be convinced it was going to tell you something really interesting about the way the planet worked. No one really knew that in advance. It just required a certain kind of curiosity and willingness to spend a lot of time building up an inventory of facts.
So this is a good argument for the funding of basic research. So when a congressman or senator says, "What good is this $100 million grant going to do?" Well, I don't know. We'll find out in 25 years. After all this information is collected, and we see what happens. But that doesn't sound good to a congressman that has a constituency they have to answer to. Why are we spending this money?
Yeah, even the funding agencies like the NSF have all of their big initiatives for funding. They say we think we should fund this program, or we need more research done on these questions. And not exactly to knock that, but at the same time, some of what's going to be really important in 20 years' time is stuff that nobody at the NSF or anywhere else has any idea will be important. So to some extent, it is a little bit like just rolling the dice, huge big buckets of dice. The more dice, the better, and to some extent, the less direction, the better.
Yeah,
I think.
right. Yeah,
we have to kind of give ourselves over a little bit to the random nature of discovery.
One of my favorite stories about Darwin is, I call this Darwin's dictum, where he says, so this is from the 1861 British Association for the Advancement of Science conference discussing the origin of species. He didn't go. And I think it was one of his friends wrote and said, they were discussing your theory. They said your book is too theoretical. Just let the facts speak for themselves. Just put it out there like a naturalist would. And he writes back and said, this would be like counting the pebbles in a geological formation. You got to have something on top of it. Then he says how odd it is that anyone should not see that all observation must be for or against some point of view if it is to be of any service. So I call it Darwin's dictum. It's one thing to have data, you need it for sure, but you need something over it. Like what's it pointing to, at least for now? And Darwin, Gould wrote an essay about this. When Darwin was on the origin on the Beagle, he had a copy of Lyell's geology textbook. And Lyell's, according to Gould anyway, I haven't read this, but Lyell's theory of reefs, there's different kinds of reefs, fringing reefs, and I don't know, there's like a dozen different kinds of reefs that you can see when you go out to the South Pacific. And so Darwin saw these, and apparently Lyell had like a different theory to explain each of the different reefs. And Darwin deduced, what if it's one mechanism and these are at different historical stages of that development, erosion and uplift and all that kind of stuff. And, and in a way that Hertzsprung-Russell diagram in astronomy, there's all these different stars, the orange stars and blue stars and white stars and so on. They're actually all the same, but at different stages of their development or their evolution or whatever. That's a pretty deep insight.
Yeah, I guess I'm wondering to what extent Darwin always followed Darwin's dictum. I mean, not that I think that he didn't have reasons for. He wasn't just he wasn't just wandering the beach, gathering pebbles. He knew some things were just inherently more interesting than others. But it seems to me he he had such Catholic interests. He's just interested in so many different things. It's not quite. And then some of the things he was doing, he really was doing because he had this big theory, and he was trying. There was some part of the theory he wanted to investigate further. But I don't know. He strikes me as a scientist who was so successful in part because he just got really interested in so many different things without having to have to tell himself a story about why it was worth paying attention to them.
Interesting. Yeah. Yeah, I don't know, but
So I don't want to say, not a pebble gatherer perhaps,
yes.
but still somebody who's just kind of likes the beach for its own sake.
Well, there's that, and also there's a kind of a survivorship bias in these stories. We're picking out the most successful theories that turned out to be right, and we go, oh, okay, how did he figure that out? And then the hindsight bias, we look back, oh, he did this and this and this and this. What about all the failed theories that people had that we don't even know what they are because they never got published or they never panned out into anything? No scientist ever picked them up and used them, and they're just gone.
That's why we need history of science, or one of the reasons we need history of science is to give ourselves a little bit of that perspective. Yes, because I think what you say is very true. And all the big storehouses of empirical data that turned out to be not very helpful for figuring out anything. There are those too.
Yeah, that's right.
But science is in some ways a high-risk activity.
So we have this kind of idealized version of science where you make your predictions and then you run the experiment and test it and see if it's true or not, or it's not falsified or whatever. But my favorite chapter in your book is on the whole Eddington eclipse experiments to test Einstein's theory of relativity. In pretty much every textbook, it comes out like, oh, it was this super experiment, and that confirmed it. Einstein is, on the cover of the New York Times, and all the lights askew, the New York Times says, and now he's world famous. But the story is way more complicated than that. So give us the whole story because it's so interesting.
Oh, okay, yeah. So Einstein presented the final version of his general theory of relativity, his theory of gravity, right in the middle of World War I. So not a very propitious time for doing basic science. Eddington, who was a British scientist, so technically Einstein's enemy, the enemy of the German scientist, was one of the first people to appreciate Einstein's theory. Eddington was a very talented mathematician. I think he was actually the first Wrangler at Cambridge, so the star mathematics student of his year at Cambridge. So he could get into the complex mathematics and just see how well it worked. In particular, at answering questions that maybe nobody ever thought would be answered. Why gravitational mass, that is the mass that determines the degree to which you will be attracted or attract another mass, is exactly equal to inertial mass, that is the mass that determines how reluctant you will be to get moving when you're given a push. The fact that these two are identical, that's at the bottom of Newton's physics, but it's not explained. They could be different properties. And one of the things that Einstein achieved just entirely in his theory was to explain why they're the same. Anyway, that's exactly the sort of thing that appealed to a thinker like Eddington. But as I've said, science is all about empirical argument. If Eddington was going to convince the rest of the world that Einstein's theory was to be taken seriously, and actually one reason he really wanted to do this was he himself was a Quaker and basically a pacifist, and he was horrified by a kind of a rift between British and German science that was spreading as a result of the war and even continued after the war. So he very much also had a kind of universalistic urge in his investigations. But he realized that neither a quest for peace nor a quest to provide an esoteric theoretical explanation for the equivalence of the two masses was going to count for anything in convincing other scientists, or at least convincing them officially. What was needed was some sort of empirical test. Einstein himself had said this. There was one empirical test already, which is that Einstein's theory explained a certain anomaly, or an anomaly from the Newtonian point of view, with the orbit of Mercury. But more tests were urgently needed. One of these tests would be to measure the degree to which gravity bends light rays, or diverts photons, if you like. So Einstein's theory predicted more bending than would have been expected on the basis of the classical physics that came before Einstein. And the way to test this theory was to get light to pass very close to a very large object and see how much the light was bent. But you need a really big object. In fact, you really need the biggest object around, which is the sun. So what Eddington's idea, and the idea actually of several scientists at this time, was to look at stars that were very close to the sun at some particular point during the day. So as the sun got very close to the star, so the light ray from the sun is going from the star is going right past the sun, and see to what extent it looks like the star actually is displaced from the sun, which would show how much the light ray is being bent. Only problem, of course, is that the sun is extremely bright. So you really need something to shadow the light of the sun while you do this this measurement. And the perfect candidate for doing that job is the moon in the course of a total solar eclipse. So this turns into a very complicated experiment. You have to find a total solar eclipse. They don't happen very often. They don't last very long, just a few minutes typically at the moment of totality. Photograph the stars right in the vicinity of the sun, and then compare those photographs to a picture of the very same stars when the sun is nowhere near them. And then you'll see the stars with the sun being shifted out just a little bit, but a tiny amount, on the order of about a 60th of a millimeter, believe it or not. So you might think, how could you even possibly measure that?
Yeah.
But Eddington was confident that he could achieve that kind of precision. Anyway, by looking at that very slight difference, and this is exactly the kind of detail I say decides the question between two great theories. By looking at that tiny little detail, you could decide whether Einstein or Newton is right. And of course, Eddington very much wanted to show that Einstein is right. So he himself, although he wasn't really much of an experimentalist, he seems to have had a very ignominious career in the Cavendish lab at Cambridge when he was briefly working there, led this experiment, sailed off to the equatorial regions where the next big and a very favorable eclipse was going to occur. Favorable in the sense that at the moment of totality, the stars behind the sun would be relatively bright, so that they would show up better on a photographic plate, and these tiny little discrepancies would be easier to measure. Anyway, so he took two teams off. He himself went to Principe, the island just off the west coast of Africa, and his collaborators went off to the northeast of Brazil. Both places that are in the very narrow track where the eclipse was going to be total. They had 3 telescopes with them total. There were 2 in Brazil. So in my story, I just focus on the 2 in Brazil. Actually, it was rather cloudy in Principe. Another good illustration of the riskiness of science. You have a 6-month expedition to photograph the sun during these very 5 minutes of total solar eclipse, and then it's cloudy. And Eddington, as he noted ruefully in his notebooks, 5 minutes later, the clouds had cleared, but it was too late. So the data from Principe was not great. He managed to do something with it, but the real data was coming from Brazil. 2 telescopes, both photographing the stars. What happens? They disagree with one another. One of them brings back results that actually reflect Einstein's predictions quite well, but the other one comes back with results that are almost exactly what you would expect if the old classical theory were right and Einstein were wrong. Well, but there's one more important thing. The telescope that is unfavorable to Einstein, if you like, the Newtonian telescope, the images from that telescope are also somewhat blurry. So something went wrong with the telescope, and it was a bit like the clouds in Principe. It was back working perfectly the next day, or when they next were able to go back and figure out what was going on. So it was just this frustrating little glitch that caused something to go wrong, and the stars went blurry. Question: does that invalidate the data from the telescope? Well, if it were just a slight defocusing, then insofar as you could still measure a little difference between the stars with and without the sun, which you could, and as I said, these measurements, in fact, looked like they would undermine Einstein, that would be really useful information, and that would be information that would really sow some doubts about whether Einstein was right, even as the other telescope was saying exactly the opposite. But another thing that could have happened is that the results could have been systematically distorted in a certain way. And if that were the case, then of course they could be distorted in a way that really just got the measurement systematically wrong and made Newton look right and Einstein look wrong, even though Einstein was right. So the Eddington team was faced with a kind of dilemma. What do they do with these results? They have some reason to think that clearly something went wrong, but it could have gone wrong in a way that made the data still useful and informative in a way that would have weakened the case for Einstein's theory, or it could have gone wrong in a way that really made the data basically useless. Anyway, although the paper that reports the result of the eclipses very faithfully and accurately reports everything I've just told you, including the fact that they got these results which were unfavorable to Einstein. They report on the blurring, and they say, truthfully, we don't know what the cause was, and so we can't say whether this is the kind of problem that would make the data worthless, or whether it's actually telling us something that we don't really want to hear. But then, in a dramatic turn, without any further comment, they just decide that the data from this telescope will be disregarded, and that by the end of the paper, they're saying clearly these results show that Einstein is right.
Wow.
So there's a lot of interesting lessons about science in there, including perhaps above all the importance of subjective judgment calls that not every scientist is going to make in the same way in deciding how to interpret evidence. I mean, experiments almost never go perfectly. And so there's a lot of these judgment calls. In the long term, science seems to, on the whole, get things right. But in the short term, it can be really confusing to say exactly what the evidence is telling you.
Yeah, in this case, it's not like you could just set up the conditions the next day and run it again. This is a natural experiment. It's not going to happen very often. Right. So
exactly.
But ultimately,
well, in the end, they did. Go on.
No, I was just going to ask that. Okay, so how do we know that Einstein's right?
Well, because scientists are very patient, or at least they have no choice but to be very patient. And they went out and they did the eclipse measurements again the next time a good eclipse came along, and again. And then they refined the machinery a little bit so that they could get even cleaner data. And over time, there are a whole series of sets of measurements from different star fields and different eclipses. And the great majority of those results showed what Einstein predicted. So it was a sort of slow, patient accumulation of data that, in the end, undergirded Einstein's theory, and also some other measurements as well of a different phenomena. But which again, those ones though took a while to come in. So there was, now we look back at Einstein 1916 or 1915-16 when Einstein proposed his theory, and the dramatic eclipse experiment of 1919. That's when Eddington did these measurements as confirming Einstein, but it was a lot more complicated than that. And for some time after Einstein proposed his theory, it was perfectly reasonable for scientists to say, well, I don't know, we've gotten the evidence is somewhat sparse, and it's a little bit mixed as well. I'm going to wait to make up my mind until I hear more.
Mm-hmm. Yeah, and then that was that eclipse experiment in 1916, where the Germans went to Russia, where there was an eclipse, but that was during the war, and they got arrested as spies, German spies.
That's right.
And do I recall Einstein had to help bail them out or something like that?
Oh,
I don't remember how they
that's
got back.
possible.
I don't think
sure.
they were killed or imprisoned forever. But again, part of the kind of dirtier side of science you don't often hear about. Right. So, outsiders don't see all that. And, I get a lot of these theories of everything that I'm sure you get, and famous physicists at Caltech and MIT get them like all the time. That is, people have worked out in their head or in their garage or whatever, a new theory of the universe. It's almost always a physics thing. Rarely is it like chemistry or some other technical problem. And it's kind of this grand theorizing. And Einstein had this dream, right? He dreaming of riding on a beam of light and dreaming of falling in an elevator, and the pin and him are falling at the same rate. So that's what it would be like in space, something like that. And, I have dreams like that. Why can't I be Einstein? And I guess your answer would probably be, well, you could be. Go ahead and spend the next 20 years running experiments and see if you're right.
Absolutely. Yeah. Einstein actually is really a terrible model of a scientist. I mean, of course, he was brilliant and achieved things in a way that does hark back a little bit to the old Aristotelian way of
Mm,
proceeding. There's
mm.
this, I think the big volume uh, tribute to Einstein that philosophers put together many years ago was called Albert Einstein, Philosopher Scientist. Of course, what greater praise could there be? But he was a little bit philosophical. This is one of the reasons I think why he never accepted quantum mechanics, where the physicists around him were prepared to say, "Yeah, sure, I don't. None of this. If we subject this to any kind of philosophical test for intelligibility, it's puzzling and really highly dubious. But it's also a mathematical theory that makes very exact predictions which come out right. And as scientists, this is going back to the whole Newton project, the experimental philosophy. As scientists, that's what we care about. If we can't understand it, too bad. As long as it's getting the right results, we're all in. And
Right,
Einstein did not go along with that, and that was a sign that he was not, in a way, a fully modern scientist.
right. I also like to point out that he did publish in mainstream peer-reviewed German science journals. It's not like he's just making this stuff up on the fly.
Yes, right.
He was not instantly accepted, and a lot of the anti-Semitic German scientists didn't like Einstein. That was kind of a Jewish kind of science, so there was all that ugliness as well. I was wondering if I have here Leonard Mlodinow's memoir and biography of Stephen Hawking, really just a memoir of working with him, because you quote both Mlodinow and Hawking. They have this idea they present in this book, The Grand Design, that they call model-dependent realism. So here's what Leonard writes describing this. In physics, a theory is either true or it isn't. A philosopher would say we physicists use that word sloppily because all truth in physics is provisional. You can never be sure that a future experiment won't come along and contradict your hitherto perfect theory. But what I mean by a theory is either true or it isn't is that in fundamental physics, at least, there is no almost right. If a theory fails even a single obscure test, by even the tiniest amounts, we say the theory has been falsified. It cannot represent the true laws of nature. So then he goes on to talk about, they developed this model to explain whatever it was they're trying to explain in the grand design, the origins of the Big Bang and string theory and all that stuff. And they're not claiming anything deep about the universe. It's like, this is our model. Does it predict what we find if we run experiments? If it does, then it's a good model. If it doesn't, then it's a bad model. Is that kind of what you mean about the way science works?
Yeah, yeah. No, that's exactly what I mean. With the one proviso that although that falsification is not as easy as it sounds.
Yes,
I mean, something
yes,
like the Eddington story gives you a
yes.
good shows why. You never know when your instruments are working properly, when they're not. Probably it's the case that usually in science, I mean, science really at the cutting edge, your instruments are not working properly, and it's on rare occasions when everything goes right that you gather the data that really matters. So, although technically, maybe I should say logically, um, it should take just a single measurement of the bending angle of light to decide whether Einstein is right or wrong, or at least right or wrong about that. Um, the way it really works itself out is, as we were just saying, for many years, there's a lot of disagreement. People aren't sure what to think because there are complicating factors in the way the data is obtained. And that's so often the case. But that said, scientists, as I say, they go back, they make the measurements again as best they're able. They spend more money, they throw more ingenuity at it, and in the end, they do tend to accumulate enough of an experimental record that we can say, yeah, this theory really just gets that wrong.
Right. Okay, I was gonna.
And therefore we can treat it as falsified.
While I'm
Uh,
with Leonard's memoir, I note your book on page 260. You have 3 quotes from scientists saying philosophy is dead, which I'm glad you had because
mhm.
philosophers are not crazy about hearing these sorts of things. You have Stephen Hawking and Leonard Mlodinow in the Grand Design I just quoted from. Philosophy is dead. Philosophy is not kept up with modern developments in science, particularly physics. Scientists have become the bearers of the torch of discovery in our quest for knowledge. And then you quote Neil deGrasse Tyson saying something similar, and the physicist Lawrence Krauss saying something similar as well. And you properly upbraid them. But I have a funny story for you. So I had heard the story from Len before because I asked him about that when those stories broke. So in his memoir, here's how he describes how that sentence got written. Excuse me. Let's see. When Stephen's pill regimen finished, so he's described going over there to England. He has to sit there for hours and hours when they get him ready, and he brings in. It takes forever to communicate with him because of the disability and so on. So Leonard says, I finally got to pop my question. Why do you want to write that philosophy is dead? I asked him. It's not dead. What used to be called natural philosophy is dead, but not philosophy. And then he writes, natural philosophy was a precursor to the sciences. Anyway, he has a little history of that. Then he goes, let's see. I agree that today we can understand the universe better through science than philosophy, I said, but there's also the philosophy of life, there's ethics, there's logic, there's philosophy of individual disciplines such as mathematics and physics. Those branches of philosophy are not dead. And then he writes, Stephen gave me a critical look. He obviously saw things differently. As I waited his response, I gazed idly at him. Suddenly, it struck me that the sport jacket he was wearing was a couple sizes too big. He seemed lost in it. And in his slacks, too. I suppose that well-fitting clothes would be difficult to find for him, given his almost complete lack of muscle. There wasn't much meat on his bones. I have an idea, I said to Stephen. He stopped composing his answer and turned his eyes to me. How about writing, as a way of understanding the physical world, philosophy is dead? Stephen grimaced. He looked back at his computer screen and resumed working on his response. Impatient for his reaction, I got up and walked around to watch what he typed. It felt a bit funny, as I wasn't accustomed to doing that, and I'd been warned that he generally didn't like it. But on this occasion, he didn't seem to mind. In time, he'd grown comfortable with my pulling up a chair to sit beside him. Anyway, so let's see. The text finally comes up. Your sentence has no punch. And then Len says, I answered before he had a chance to make his computer voice. That's true, I said. It's less punchy, but to say philosophy is dead is an oversimplification. Hawking looked back at his computer screen, but didn't type anything new. Just had his computer voice, a voice to what he had just written. Your sentence has no punch. And he says, I do get what you're saying, I told him, but if we say philosophy is dead, we'll piss off a lot of people. And he just typed it again. Your sentence has no punch. And that was it. So that's how they ended up with that sentence. And Stephen Hawking, when, at that point, when he speaks, he decides that's it.
Indeed, yes. Well, as I say in the book, actually, I think in a way I have a more favorable interpretation of what they're up to than many philosophers. I see those claims. I mean, interpreted literally, I think that it's unfair to philosophers and philosophers of physics in particular, who certainly have kept up with what's going on. But I see those as more a kind of exhortation to the troops, to the scientists, telling them, don't philosophize, just pay attention to the data. And that is the way that science should be done. So it's a kind of it's a kind of revving up the workers, I suppose, to keep their minds focused on the right way of doing science and not get distracted by philosophizing. And insofar as science does work that way, I think that I might prefer that this job be done without disparaging philosophers, but it's a job worth doing.
Right. So let's talk about consensus in science. So, now there is consensus that Einstein was right and Newton was wrong about the bending of light. Okay. And that just took enough experiments. But there's always anomalies in any theory where, there's a few little things over here that the theory doesn't explain. We just sort of set those aside. We assign them to graduate students to figure out or whatever. But, to the general public, they'll come up with, well, did you see that study published about glaciers or sunspots? And doesn't that override the consensus about climate change? Or, there was that study on ivermectin or the vaccines or the masks or, and it's like, okay, I don't know that particular study. So I don't know how to respond to that, and so there's never going to be 100% consensus. And any outsider can always find this one guy over here that says, no, I don't believe in climate change, as anthropogenic global warming or whatever. How do you, as a philosopher of science, think about how do we reach consensus? How do you know that, this is very probably the case?
Well, the unfortunate truth is that it does take a long time often to reach consensus, and certainly it takes too long for us to wait for complete consensus to emerge before doing something. COVID is and the response to COVID is the most salient example of this. Even much more so than climate change, where although we don't have that much time, we have at least some time to wait and see. But with COVID, we kind of needed the answers yesterday. And what was coming out of the scientific process, as is so often the case, was contradictory data that required a lot of interpretation, a certain amount of expertise, and perhaps some knowledge of the kinds of even quite detailed knowledge of where the data was coming from that no ordinary person could reasonably be expected to have. And scientific knowledge is chaotic. In the sense that when it's being made, it's chaotic. There is periods, often quite long periods, when there's great disagreement about how to interpret the data, which data really matters, and which is going to be one of those anomalies that gets solved way down the line, but not something to worry about right now. Scientists disagree about. I mean, scientists will think so-and-so's lab just produces very, very fishy results. I mean, maybe not fraudulent, but they're just not very good experimentalists over there. So I wouldn't weigh what they do very heavily. But so-and-so's lab over here, they're really reliable. And if they're getting this correlation, this connection, then I'm paying attention. And, that requires a tremendous amount of insider knowledge. You not only do you have to be a scientist, you have to be a scientist in that very area and to have been around for a while to form these opinions and to understand that other people are forming them and to know what kinds of opinions they have. So the state of knowledge at these times when we really would like to hear some big booming voice come down from the heavens saying, science has now discovered that COVID is transmitted by aerosols. Mask in the following circumstances. We're just not going to hear that voice until it's too late. So we need some kind of different process for dealing with the dissensus. As I say, I think typically, although it can take a very long time, consensus does emerge from a long cumulative process which gradually leans one way rather than the other on various crucial questions. But it's not what you would hope for from our premier knowledge-producing machine. I mean, it's the best we have. It's probably more than we deserve, but it's not. There is no voice of science sitting there that's going to advise us on these things. No one is really in a position, actually, to figure out at any particular time what we really know, except about things that have been settled for so long that it's no longer an issue anyway.
Yeah, it's a nice distinction between climate change and COVID-19. I mean, in the case of COVID-19, you have somebody whose job it is, and not just Anthony Fauci, but other people, and you go to a press conference and they stick a mic in your face and go, what do we do tomorrow? Do we close the restaurants tomorrow or do we open them? What's your answer? It's not like Al Gore giving his lecture about climate change. We have 40 years to figure this out. It's like, I kind of feel sorry for those guys. And, I'm frustrated at Anthony Fauci constantly changes his mind, but I can understand why. He can't just give some Bayesian reasoning. Well, maybe this, maybe that, who knows? I don't know. Let's wait and see. Right. And then the poor politician says, well, okay, then we're not going to close anything down. And then next thing you know, half the city is dead. And then he's in trouble, right? Because he didn't do anything.
So true. Yeah. I mean, of course, and there's this whole other dimension of public policy here. Above and beyond interpreting the science is the question of what the right thing to do, even in the light of the knowledge, is. But the problem begins simply with the uncertainty of the knowledge itself, and in the kind of the in a responsible, you see a responsible scientist changing their mind, and in some sense, that's the reasonable response to the changing situation on the ground as far as what's been discovered and what's still up in the air. So part of the problem of kind of making science useful to society is creating a kind of interface that is capable of interpreting the science, not over-interpreting it, but interpreting it and and communicating some of it to the general public in a form that's not too misleading and not too confusing at the same time.
Right. Right. I was at this conference last year, Freedom Fest, and kind of a libertarian conference. So they cut both ways on science. And anyway, one of the speakers gave a talk on, was talking about Anthony Fauci and COVID and so on. And so he starts on this story about this paper published in, I think it was like 1980, 81 or 82. It was in the kind of the height of the AIDS virus pandemic coming online. And said, look, in the journal Nature published this study, or it might have been JAMA, saying that AIDS can be transmitted through the air or through water, and then it was refuted, like within a week that can't be the case. And the author of this paper was none other than Anthony Fauci. It was like, okay, so he retracted it because they had better information. That's kind of how it works. But again, it's like picking the guy that who made him God to tell us what to do. Like, well, that's his job. I mean, we want somebody at that job, right?
And we want scientists to do what he was doing back in those days, to be charging off in every direction, trying out every plausible hypothesis, testing every hypothesis, not kind of thinking ahead to what people are going to be saying about them 20 years later.
Yeah.
I think that would be kind of disastrous if you knew you were going to be subjected to that kind of scrutiny. It would really shut down. I mean, of course, in most areas, nothing is controversial enough to really have to worry about blowback from the public. But it's important that science can be experimental intellectually as well as in the usual way.
Mm-hmm. Yeah. Right. So, we have this idea that if it's published in a peer-reviewed journal, well, then that's it. Well, that's just the start. Good luck with that. There was that line, I forget who said this, 90% of what's in textbooks is probably true. 90% of what's in peer-reviewed journals is probably false, right? It's just a first step. And
it's part of a bigger system.
Right. So, and again, I've been guilty of this, psychics and people who believe in the paranormal and the supernatural and psi and all that stuff. Well, what do we got to do to convince you? Well, a controlled experiment, published in a peer-reviewed journal, and so on and so forth. Okay, well then I've asked you about this before when you gave a talk here at Santa Barbara. Okay, here's Daryl Bem published this study on backward causality of psychic, kind of anticipating what's coming up on the computer screen, published in this very respectable peer-reviewed journal. Now, what do you say to that? And it's like, well, let's run it again.
Yeah. And that is, in fact, how science works. Everyone will look at that and say, let's run it again.
Yeah, so I mean,
and there's no single test that's going to decide things one way or the other.
Right. Yeah, so there, I guess we'd employ the ECRI principle: extraordinary claims require extraordinary evidence. So if your scientific theory is just some little thing that wouldn't surprise anybody if it was true, probably we're not going to put huge demands on you. But if you're saying like all of physics is wrong and effects can cause causes, kind of reverse backwards in time, which this experiment purports to show, that it's sort of a Bayesian thing. Like, I don't know, my priors are pretty low that you're right, so we better have a bunch of experiments, right? And so that's what happened there. That Stuart Ritchie and Richard Wiseman tried to replicate Bem's experiment, and they failed to replicate, and they submitted it to the Journal of Personality and Social Psychology, and they rejected it, saying we're not interested in failed to replicate studies. It's like, well, that's a problem.
It is. Yeah. One way in which it's not as big a problem as people sometimes think is that there's a lot of failed replication that goes on and doesn't get published, but which becomes well known among the scientists who really need to know about it. Now, of course, that's not going to help when the study that goes unrefuted is, something about vaccines and autism or something like that really has an impact in the wider world. But for the most part, the scientists kind of know what's going on, and so the sum total of knowledge that scientists have is more than just in the journals. Another, which is another illustration of what I was saying earlier, that it's really difficult to kind of just look and see what science knows, what science has discovered. Some of that information is not being published. And of course, the people who want more failed replications, negative results to be published, are thinking precisely this. We need that to be in the public record, not just in the heads of the people who it matters to most.
Right, the file drawer problem. But the scientists know what's in the file drawers because they talk to each other, or the labs communicate with each other, or they meet at conferences. This is my answer to the, it's a kind of a conspiracy theory that climate scientists are all in cahoots together because they're liberals and they don't like capitalism, whatever the argument is. Right. Well, these are people that are very competitive. They would love to debunk each other's ideas, right? And in most cases, they don't even know each other. They work in different fields. If you're studying glaciers and somebody else is studying clouds and somebody else studying sunspot activity and somebody studies the migratory behavior of birds that are migrating earlier and earlier because it's getting warmer earlier and so on, they don't meet with each other. They don't know each other. There's no way there could be a conspiracy, even an unconscious one.
Absolutely. That's the flip side of the chaotic nature of scientific knowledge, is to organize something that chaotic to the degree that would be required to tell the story about the non-existence or something like that about climate change. That would require a conspiracy on the same level as the nuttiest conspiracy theories in the history of conspiracy theorizing. It really, to anyone who has a sense of how science works, it looks crazy.
Yeah, I use the same arguments against creationists because they have this idea. Well, they've all bought into this materialistic, atheistic worldview, so they have to support the Darwinian theory and all that. But if you have geologists or paleontologists or botanists, comparative anatomists, zoologists, these are different fields, and it's not like they're all meeting on the weekends to get the story straight because we got to, reinforce the materialistic, atheistic worldview, right?
Right.
Yeah, but and again, they're competitive, right? I mean, one way to advance in science is to debunk some famous theory, and like you made your name by overturning this accepted dogma, right?
Right. Look at all the physicists who are desperate to have some result coming out of places like CERN that will overturn the standard model. There's nothing they would like more in that case, and nothing they would like more than to be the one who kind of turns it into the refutation.
Yeah.
Because there is so much to gain.
Yeah, I belong to this group called the Galileo Project, run by Avi Loeb at Harvard, that's going to try to get to the core of what these UAP videos are, the unidentified aerial phenomenon, so-called UFOs. Right, so there's a lot of these, I don't know, a dozen or so of these grainy videos and blurry photos. What are they, right? So Avi wants to set up like hundreds of telescopes all over the world, and with acoustic recording devices. Let's see what it is, right? Because there's so few of these, comparatively speaking. And anyway, one of these discussions, it went off the left turn there about, this object seems to veer off to the left so quickly, it must have some completely new kind of physics working there. And Avi says, okay, hang on for a second. There's no new physics, right? We just spent $1 billion at the CERN particle accelerator. They didn't find any new physics, right? Let's not go down that path. Let's just see if we can take better pictures of whatever it is we think this blurry thing is, right? So again, it's like some Navy pilot shoots a video. What's more likely, that all of 400 years of physics has been overturned by this guy with a video camera, or that he just didn't see what he thinks he saw?
No, indeed, yeah, and I guess one of the reasons I wrote this book is to write something for the general public that would give people a little bit better of a sense of, as I have been putting it, the chaos of scientific knowledge. It's not, of course, a book that's primarily about the communication of science, but just having a sense for how science works internally, and the state of constant disagreement, conflicting interpretations, and so on, which is just completely normal and natural. I think if people understood that science works that way when it's working normally, then they wouldn't be so, they might be disappointed, but they wouldn't be so inclined to think that something had gone horribly wrong with science when they get a little bit of a taste of that from looking, say, at what was coming at us, especially in the early stages of the COVID pandemic and so on. Just have a somewhat more realistic expectation for what kind of consensus can be built in science and what can't be built in a certain time frame.
Okay, a couple last big questions. What are the limits of science? To what extent can science say something about morality or meaning of life, or what religion typically deals with, like what was there before the Big Bang? Where did all this stuff come from that banged in the Big Bang? Why is there something rather than nothing? How do you think about to what extent science can push those boundaries?
Well, I'm on the one hand, I'm a naturalist myself, and that I think the material world is all there is, and so best techniques for knowing about the material world will answer those kinds of questions if anything can, or at least that's my prejudice. uh, on the other hand, this work I've done on the nature of science, one thing it's driven home to me is that science's success comes from a certain kind of narrowness, from the exclusion of certain ways of thinking. It's possible that we need those ways of thinking to complete the story about some questions. So maybe we will need to go back to a more Aristotelian, or for that matter, Einsteinian way of thinking about what really makes sense physically to answer those questions. It could also turn out to be completely useless to think that way. It's not as if I have any inkling myself. But seeing science as a very particular kind of, if you like, technology, social technology, um, raises the question, as the same question that should be asked for any technology, of what kinds of things it might not be good at doing. Things perhaps that can be done that science isn't quite the right tool for, something where we really will need the Aristotle and not the Newton. Again, I'm afraid I can't follow that up with any insights of my own to demonstrate the value of philosophical science. But
Well, here though, it seems like
certainly an interesting
if you
possibility.
push the science deep enough, you end up back in philosophy, right? Like I was writing about the question of why there's something rather than nothing. So I found this great quote from John Leslie and Robert Lawrence Kuhn in their book called "The Mystery of Existence: Why Is There Anything at All?" And so when you start thinking about something like the word nothing, what does that even mean here? I mean, we're really just in your realm of philosophy, right? So here's what they write.
Mm-hmm.
That it's almost an inconceivable idea. First, is suggested it is impossible to conceptualize nothing, no space, time, matter, light, darkness, or even any conscious beings to perceive the nothingness, as Kuhn and Leslie write. Not just emptiness, not just blankness, and not just emptiness and blankness forever, but not even the existence of emptiness, and not even the meaning of blankness, and there is no forever. At this point, I don't even know what these words mean anymore. I'm just like, what are we even talking about? you know, how would you get at that scientifically? Okay, so you're a philosopher. At some point, what I'm wondering is, are we hitting like Wittgenstein? Are we just hitting the limits of our language and cognition, and we just can't go any further?
Well, maybe so. I mean, that's a good example of the kind of application of philosophy that I have in mind. So I'm not endorsing that particular argument, but you could discover that the very concept of nothing is incoherent. So it turns out that we can't fail to explain why something comes from nothing, because we can't even frame the question. We've confused ourselves in even posing the question in exactly the way that Wittgenstein would love to tell us, because he loved to tell people that language had tripped them up. That's these kinds of arguments are the kinds of arguments that can't really appear in scientific journals the way that science is currently constituted. So we'd have to, if you were going to push science in that direction, or kind of open that kind of direction of thinking up to science, you'd have to change the rules of science itself. Maybe another example of this is what people call anthropic reasoning, where you say, well, all the constants in our physical theories are tuned to just exactly these values that allow life to exist, and try to draw some conclusion, essentially philosophically, from that observation. So it's an interesting form of argument, and there may well be something to it, but it's not the kind of argument that is a legitimate scientific argument, because it's not an argument from empirical testing. I mean, we know the values of the constants from empirical testing, of course, but then the next step, the what are the chances step, is, I think, just takes us outside of the narrow sphere of science proper. But then maybe it might well be worth going there, and that would be a place where philosophy could come back and allow us to make a few further steps down the road to figuring the universe out by departing from the standard scientific procedure.
Right. As you know, theists and creationists and intelligent design theorists have specific what they think is scientific-based arguments. You just mentioned one, the fine-tunedness of the universe, and they have half a dozen of these. Would anybody before Newton have made arguments like that? Like, would anybody say, how do you know there is a God? Or how do you know that God created the universe? Well, here's our six empirical evidence, the fine-tunedness and this and so. So I'm just kind of speculating here. Maybe pre-Newton, that's just wouldn't have entered anybody's mind.
Well, I suppose that, I mean, even until really relatively recently, maybe the 19th century, it's full-on atheism was I think considered by people like us, and by people like us, I mean just people who occupied our station in society, would be regarded the same way we regard the conspiracy theorists. That's a possible view. Some people who defend it in this extremely clever way, but obviously it's wrong. And so the whole business of constructing arguments for the existence of a creator or something like that, although people did indulge in it, it was more of a kind of intellectual exercise, or it was a kind of buttressing of the faith that already existed. And in that sense, there was nothing really at stake. Although many writers were kind of enjoyed pointing out the evidence for God's existence, let's say, in the way that the solar system is designed or the way that life is created. It wasn't as if this was necessary in order to stem the flow of the tides of atheism until, for many different reasons, I suppose, the 1800s.
Interesting.
And for that reason, I think it's hard to pose this question in a way that has the same resonance that it does today. I mean, people did construct arguments for the existence of God, but it wasn't addressing genuine doubt.
Interesting. Right. So Aquinas' 5 proofs for God, something like that. Professional philosophers were able to make these arguments, but the average person probably didn't feel the need to make an argument. Like, well, of course there's a God. What are you talking about? Everybody knows that. Something like that.
Right, and even for Aquinas himself and his fellow monks, I take it that there wasn't any serious doubt about this. The point of constructing the arguments was just to show that reason was in harmony with revelation, if you like.
Right. Yes. Right. The historian Keith Thomas makes this point about the rise of witchcraft and supernatural elements like ghosts and demons. Right at the time science was really gaining momentum and getting a lot of respect, and his argument was that, if we disprove the existence of witches, then maybe there's no demons, and if there's no demons, maybe there's no God. So we better get to work at finding evidence for these witches, and that led to all these crazy tests. If she sings, she's innocent, and if she floats, she's guilty, and or searching the body for the signs of the devil and all that kind of crazy stuff. But that was kind of a drive to find evidence. Why? Because science was becoming respectable, and you got to have evidence for your beliefs.
Yeah. Maybe can I add something about the fine-tuning thing?
Yeah.
One use of the fine-tuning fact is to kind of build a bridge to God, but another is to argue for the existence of the multiverse. This the idea that there are actually many parallel universes,
Right.
each has their own set of physical parameters. Why is ours uniquely suited to life? Because we wouldn't be around uh, if it weren't. Wherever there is life, there is one of these universes where the parameters are right, and we should still be surprised that we exist, that there is any such universe at all. But that surprise is assuaged by realizing that all possible universes exist.
Yeah, so I
Um,
make that argument
this is the
I make that argument to theists, and they come back and say that's just faith. Come on, you don't know that that's true. There's no experiment you're going to run. You're not going to
uh-huh.
get any data to test that. That's
Yeah.
just your faith.
Well, to some extent, that's true. Um, but I would like to distinguish on the one hand the fact that there's no scientific evidence for that, and on the other hand the idea that there's no argument for that,
Mm.
because as I've been saying all along, those are not the same thing. On the one hand, we can't use this very specific form of argument, specific and incredibly powerful, the empirical argument to establish the existence of these parallel universes. Um, well, technically, there's something you could do that kind of virtually impossible to set up. But anyway, right now it's beyond our means to do any kind of experiment like that. But what we can do is construct a kind of probably not every scientist would want to call it a philosophical argument, but a non-empirical argument, an argument from reason to tell us something additional about the way the universe works. And that's the kind of thing I have in mind, more so than an argument for the existence of a creator. When I say maybe adding a few drops of philosophy back to science could enable us to travel a few extra steps.
Mm-hmm. Yes. Well, it'll be interesting. So you wrote this book about 350 years after Newton. So it'll be interesting to see if 350 years from now, people look back and go, "Oh, look at that crazy conversation these two guys had about what they thought science is. Now we know whatever." You and I can't even think of what they'd be thinking about, right? Maybe, I don't know. It seems like Newton figured out a lot, and that's not likely to be reversed. Maybe added on a little bit or whatever. I think I'll wrap this up by reading the last paragraph of your book, which I really loved, about what science is. It's a social institution. It cannot be brought into existence by a celestial body or a magical incantation. Inquirers had to give the rule that constitutes the scientific institution to themselves. But the iron rule is a peculiar mix of power and perversity. Logically, it is beyond the pale. It would take an exceedingly long time for social, political, and moral conditions to twine themselves into a perspective from which the rule would seem to be an acceptable idea, fit to enter the halls of inquiry. Now we know, and because of the iron rule, we can go on knowing more and more. Let's hope that knowledge saves us. Indeed. Michael Strevens, thank you for your book. Thanks for that beautiful writing and inspirational ending. And thanks for coming on and talking to me for an hour and a half. Really interesting stuff.
Well, thanks for inviting me, Michael. That was a lot of fun.